Assalamu alaikum wa rahmatullah, and good afternoon for everybody. For today, inshallah, we are going to take the introduction of the IPv6 networks. So for this topic, actually, we have many points. Actually, the IPv4 was used for many years, but due to the limitation of the length of the IPv4, it becomes not enough for all people around the world, especially after the introduction of Internet of Things. Because now in every place, for every device, at every home, we need a lot of public IP addresses. So IPv4 is no more enough. That's why they introduced the IPv6. IPv6 is has been introduced for many years also, and it's still under research. It's used in some places only for limited use, but it's ready actually for real implementation. Now, to solve the issue of the IPv4, they use something called NAT, which is the Network Address Translation. So this one is used to utilize the IPv4 for more than one PC or more than one host. So the NAT can use one public IP address for multiple hosts using different port numbers. So this is a temporary solution for the IPv4, because as I mentioned, IPv4 is not enough anymore. That's why they come to the NAT. So IPv6 addressing architecture is a developing solution for IP to provide for the next generation of networks and beyond. So after the IPv6, everybody can use as much as he need of the public IP addresses, because the IPv6 will provide a big number of IP addresses. Later we will see how much we can get out of it. The transition to an all IPv6 architecture, while progressive, requires a major overhaul of many protocols and applications, as well as standards. Actually, the move towards IPv6, all IPv6 architecture, that means everything in the network is based on IPv6. It's not an easy task. It's still under progress, and also requires a lot of modifications in many protocols. So we have to modify the routing protocols. We have to modify the control protocols. We have to modify many things. Also, applications, a lot of applications have to be modified, as well as the infrastructure has to support the IPv6. So the IPv6 network, however, aims to resolve many limitations within the current TCP/IP suite, most notably addressing the need for integrated security measures and the streamlining of protocols to minimize overhead. So many things actually is needed. It's not only the number of IP addresses that's provided by IPv6. It's also trying to reduce the or minimize the overhead of the protocols, and also it's aimed to increase the security. A deep knowledge of the IPv6 architecture is required by engineers as IPv6 continues to evolve as an integral part of the enterprise network. So we need to learn about the IPv6, because in future it's going to be the only protocol used in the internet. So we don't know in what year they will forget about the IPv4, but it's coming. It's coming. One day we will have only the IPv6. So we have to prepare ourselves. Objectives of this class is to allow you to explain the architecture of IPv6 and also to explain the IPv6 address format and addressing types. Also to describe the process of IPv6 stateless address auto configuration. So this is the main topics that we have to cover here. The topic is not that hard, it's quite simple. Here is a comparison between the addressing in the IPv4 and IPv6. So in IPv4, the address size is 32 bits. So it can give us this number of IP addresses, which is 4,294,967,296 IP addresses. So this one is, this number is less than the population of the globe. That's why it's not enough. So if let's say for every person, if let's say every one of us have one laptop and one mobile and also wants to use, for example, some sensors at home for smart home or for IoT or something like this, if let's say we say that the average of IP addresses that's needed by everybody around the world, then the numbers should be very big enough to cover that requirements. So for IPv6, the length actually becomes 1 to 8 bits. It will give us this number that I cannot read. I don't know how to read this number. It's quite big. It's a huge number. So here I think the IP address will be more than enough for using the IoT or smart homes, smart cities, and everything. It can be covered using this number of IP addresses. So using or introducing the IPv6 will overcome the exhaustion of the limited IPv4 address space and IPv6 addressing implemented to resolve address shortages. So here I have some information here. Maybe I have to share with you. So here this IP version 4 is introduced by the organization of Internet Engineering Task Force, IETF. Actually, this organization is a very active organization. It comes up with a lot of standards, including a lot of protocols and many things. Definitely together with IEEE and other organizations. So here, is there any important points here? I don't think there is anything here. Okay, here. Eventually, however, the IP network is expected to shed its IP version 4 addressing to make way for IP version 6 and provide the addressing capacity of over 340 undecillion unique addresses. Have you heard about this before? Yes, I think this is a very big number, which is reflecting this. So it's a number with how many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 3. 12 times 3 means 36 zeros. Considered more than necessary for continued IP network growth. Along with this, address allocation by the Internet Assigned Number Authority ensures that address allocation for IP version 6 is continuous for efficient future management of IP routing tables. Actually, this is the organization that's responsible of assigning the IP address, the public or the global IP addresses for people and organizations. I don't know how many, we still have 2 absent students, only 21 of attendance. Okay, IB version 6 header format. The format of the header is, as you can see here in this slide. So we have three main fields. The first field, or the first part of the field of the header, is the IB version 6, and also we have the TCP and the data here. So why TCP and data? Because IB is needed when we transmit or send data over TCP or over UDP or whatever protocol of end-to-end communication. So this data, these two parts, will be considered as a payload for the IB version 6 header. Okay, so this one is the header of the layer 4, and this one is the data. This one is the header of the layer 3, which is the routing layer or the network layer. So the IB version 6 here is, as you can see here, we have many fields. So the first field is the version. It will include the version of the protocol. And then the second field will include the traffic class. After that, we will have the flow label and the payload length here, and also the next header, then the hop limit, and the source IP address and destination IP address. So IB version 6 header has been streamlined to reduce overhead. They try to introduce this kind of fields like traffic class, flow label, and this payload length and next header. They introduce this kind of fields only to reduce the overhead of the network. IB version 6 actually introduces a lot of new ideas. One of them is the Anycast. As you remember, or I don't know whether you still remember or you forget, using IB version 4, we have broadcast, unicast, multicast. But here in the IB version 6, we have unicast, multicast, and anycast. So unicast means the destination is only one, and the destination is determined. For the multicast, the destination is more than one, and they are not specified, I mean, precisely. So they will be determined as a range of IP addresses based on the subnet mask. And the anycast here is something similar to the broadcast with some differences. Later, we are going to explain what's the difference between them. Here, let us go through these points. I don't want to miss any important thing. The IB version 6 header required some level of expansion to accommodate the increased size of the IB address. So here, the header is already expanded. And also after this, we will have the extension here, another extension for the IB version 6. It's used only when needed. So later we will see how is it. Then here, however, many other fields that were considered redundant in many cases of packet forwarding were removed. So as I mentioned here, the IB version 6 is used to reduce the overhead. That's why many fields, which is redundant in the IB version 4, have been removed in order to simplify the overall design of the IB version 6 header and optimize the level of overhead that is necessary during each packet that is forwarded across the network. In comparison with the IB version 4 packet header, the IB version 6 packet header no longer contains an internet header length. Last time we have this internet header length, and now we don't have it. Also last time we have identifier, we have flags, fragment offset, header checksum options, padding fields. But now they remove all of this. Now the header becomes very simple, very easy to deal with. So the overhead definitely will become lower and lower. The term flow can be understood as continuous stream of unicast, multicast, or anycast packets relating to the specific application or process that originate from a given source and are transmitted to a given destination or multiple destinations. The natural behavior of a packet-switched network means that such traffic flows may be carried over multiple paths and arrive at the intended destination out of sequence. System sources are then required to resequence the packet flow before it can be processed by the upper layers. So they're still keeping the what they call it, the sequence numbers in order to keep all packets in sequence. The flow label intends to identify flow label, this one. The previous one was all about the traffic class. Traffic class can be unicast, multicast, or anycast. For the oh, this meeting will end in 10 minutes. Upgrade now. Oh. Actually, this Zoom is free. The application that I'm using is free one, so it can give us only 40 minutes for the record. That's why every time I have to cut the record, then I record again. Okay, so if I cut, I will tell you. Maybe I share with you another link if it doesn't work. Okay, let us continue. The flow label intends to identify such traffic flow together with the source and destination address fields to maintain a common path across networks for all packets associated with the traffic flow. In doing so, packets are capable of maintaining sequence over the IB network, and this optimizes process efficiency. Okay, nothing to explain about this. As IB network convergence introduces technology such as voice that relies on a circuit switched traffic flow behavior and near real-time performance. The importance of the flow label field becomes more paramount. Okay, let us see what's the extension here. The extension of the IPv6 header is, as you can see here, it's another field. This is the header that we explained in the previous slide, and this is the extension. The extension actually is used only when needed. So we have some fields here like this, TCP field, reserved, fragment offset, and reserved field here, some flags and so on. So extension headers are used to support parameters that are not required in every packet, such as fragmentation, and IPv6. IPv6 means IB security. It's a security protocol. In the IPv4, all of these fields or similar to these fields was included inside the main header. So many packets that doesn't use them. That's why the overhead is more than needed. That's why now they remove all of unnecessary fields and they make it inside an extension, or they make it as an extension of the header, and packets can use them only when needed, only to minimize the header for every packet. Okay. Now we come to the IPv6 address architecture. The architecture actually is, as I mentioned, the size is 1 to 8 bits. So it would be divided like this, as you can see here. So it will be, it will start with 2001. then after that colon, 4 fields, column, 4 fields, column, 4 fields. How many fields here? 1, 2, 3, 4, 5, 6, 7, 8. 8 fields. In every field, we have 4 digits. Actually, it's not digits, 4 characters, because this one is a hexadecimal representation. It can include numbers and letters. So IEP version 6 address consists of a prefix and an interface identifier. So the prefix is the first 2 fields. The first 2 fields. They call it IEP version 6 prefix. And the interface ID is the 6 fields, like this. This is called interface ID. Addresses are commonly displayed in hexadecimal format, so that's why we can see numbers and letters. The IB version 6 address is a 1 to 8-bit identifier that is associated with an interface or a set of interfaces, as in the case of any cast address assignment covered letter. The address notation due to size is commonly defined in hexadecimal format and written in the form of this, like this, as I explained, where the XXXX relates to the 4 hexadecimal digits that translate to a 16-bit binary value. 16-bit binary value because the hexadecimal can represent 16 values, starting from 1, 2, 3, starting from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then after that, it will take A, B, C, D, and so on. So it has 16 values. The set of 8 times 16-bit grouped hexadecimal value comprises the 1 to 8-bit IB version 6 address. The address itself is made up of an IB version 6 prefix that is used to determine the IB version 6 network, followed by an interface ID. So this is the prefix and this is the interface ID, as explained. The basic addressing scheme represents a 2-layer architecture of prefix and interface ID. However, IB version 6 address types may contain many sub-levels that enable an extensive hierarchical addressing architecture to be formed in the IB version 6 network to support effective grouping and management of users and domains. So here, because this one is very large, very huge or big number, that's why they can use it for to create an architecture, IB addressing, and whatever they can do in order to support the grouping and management of users and domains. Now we come to the IB version 6 address condensing. Due to the very large size of the IB version 6 and most of that fields of the IB version 6 is will remain unused. As you can see here, we have this field is 4 zeros here, 4 zeros here, and 4 zeros here. So that's why we they said why we don't condense the IB address to make it shorter. So instead of representing or writing all values of zeros like now, instead of the 4 zeros, they make it only 1 0 here. So it becomes smaller. It becomes smaller. As you can see here, this field 2001 remains as it is. This one has a value. It's also remained as it is, but only they remove the 0 from the left side. So only zeros, leading zeros, which is placed at the left side, they can be removed to make the address smaller, to condense the IB address. Then here for the fields that have only zeros, they can use only 1 0 here to represent them, and also 1 0 for this, 1 0 for this, 1 0 for this. Then after that, we go to the next field. We remove the leading 0. We write it as it is here. And for the other field, we should represent it as it is. We don't have any 0 to remove. So this is the first stage that we can do to shorten the IP address of the version 6. Then after that, here we can see how we can make it shorter. We can remove the leading zeros from the field, and also we can represent the 4 zeros with only 1 0 to get this kind of short IP address. Then after that, this short IP address can be also condensed more than this. So the middle zeros can be removed and replaced by the double colons here. So this field can be converted to the original one, because here we know that every field has four numbers, 4 digits. So here we easily add the 0 at the left side. Then here also we add another 0. Then we can see that we have 1 field, 2 field, 3, 4 fields. So at the middle supposed to be 4 fields with zeros. Okay, is that clear? If anything unclear, please write your questions, and later we can open the questions and we can discuss. So for now, I'm going to give you an example here. Let's say we have this number, this IP address 2001. Let me make it smaller font size. If let's say we have this number, this IP address 0254, for example, 000, 000, and 0052, 0000, and how many fields here? 3. We still have 2, 000, 0, and 2A5B, for example. So this is an IP address, as you can see, which has 1, 2, 3, 4, 5, 6, 7, 8 fields. So it's a complete IPv6 IP address. And if we want to make it shorter, what we have to do, we have to keep this as it is, because we cannot shorten anything. And we remove this 0, we remove it, we make it 254, then like this 0, like this 0, and then after that we remove these 2 leading zeros here. We remove them, we write only 52, and here we keep 10, 10, and 2A5B. So this is the IP address. Now, this is the second stage. So for the third stage, here, if we want to follow this exactly, if we want to follow this, we use this double colon operator to remove the continuous 0 fields. So in this case here, we have to write like this, 254, then like this, and after that 52, like this, and after this we have to write 2A5B. Okay, as you can see here, this one cannot be retrieved. The original IP address now cannot be retrieved. Why? Because we don't know, the other side doesn't know how many 0 fields here and how many 0 fields here. So this, if we make it like this way, we will have a problem. We can convert it like this, 0 to 5, 4. Then maybe we think that here we have 2 fields or 3 fields of zeros. We don't know. So that's why it's not easy to retrieve, to be retrieved. So this is the main fields. Now we have 1, 2, 3, 4. 1, again, 2, 3, 4 fields. So we still have 4 0 fields. We have to distribute them here. So maybe we can distribute it like 1 field here and 3 fields here. And also it can be 2 here and 2 here. Also can be 3 fields here and 1 field here. Let us make all options here that can be returned, can be retrieved. So it can be like this, 0, 0, 0, 0. And also here it can be 0, 0, 0, another 0, 0, 0, 0, another 0, 0, 0, 0. Like this. This is one option. And the other option can be like this. And the other option can be here like this, 52. So how many possible IP addresses that we can retrieve out of this? We have 1, 2, 3 possible options. That's why it's not allowed to use double colon 2 times. It's not allowed to use the double colon 2 times. So this IP address cannot be shortened like this. Cannot be shortened like this. It can be only shortened. These two zeros can be replaced by 2 colons, but the other 2's cannot be replaced by this. They have to keep this way. So this is how it will look like when we have multiple zeros separated by a value at the middle. Understood? I hope you understand what I'm explaining. So please, if you have any question, anything not clear, please ask me now. You can unmute yourself. You can open your mic and ask me a question if you want me to answer you directly. If it's clear, please write clear in the chat, in the group chat. Write clear, understood, whatever. Okay, good. Excellent. Okay, so based on my explanation here, we have the idea is like this. Leading zeros have to be removed, like now, the zeros at the left, and every field that has only zeros can be replaced by 1 0. But if we have 2 groups of subsequent zeros, we can use only the double colon 1 time, which is from the left side. The first left subsequent 0 fields can be replaced by double colon. So here the double colon can be used to compress leading zeros in an address as displayed. Okay, special syntax is available here. A double colon. This value indicates 1 or more 16-bit groups in order to enable the string size to be determined. However, they can be only appeared once. So this colon, double colon, can only appear once in the address. The double colon can be used to compress leading zeros only. Okay. Then here we can see the IP address version 6 address reservations. So exactly similar to the IP version 4, IP version 6 also have some reserved IP addresses. So the first reserved IP address is this 2000:3. This one is reserved. for the current global unicast range, And also this IP address 2001:0DB8:32. This one is similar to the subnet mask that we use for the IPv4. We can use in the IPv4 we normally use 24, 32, 8 like this. So also here we can use it in the same way. This means the first three fields from the right side is going to be used for the hosts, for the host IP addresses, and the rest of the IP, which is 128 bits minus 3, it will be used for the network ID. So here this IP address or this range, actually this one is address range, you can see. This range also reserved for documentation. This range is reserved for link local unicast address range. Link local unicast address range. So this one is used only for unicast. And this range, so whenever we see this field here, FE80, we directly know that this is a unicast for local address. And also this one, FF00/8, it's used for multicast address range. And this one is used for unspecified address. This one is similar to 0000, the one that we use in IPv4. So here, this one /128, it's something similar to 0000 slash or with subnet mask 0000. Very similar. Okay. So this means anything. If you remember, we have one application to use this unspecified IP address. This unspecified IP address can be used only for the default gateway. Default gateway. So whenever we have unspecified or unknown IP address target or target IP address, we forward it to the default gateway. So in the IPv4 we use this. In the IPv6 we use this instead. And also we have this kind of range, which is a loopback address. Loopback address. So when the IP address is end by 1 like this, it will be an IP address of loopback. Address ranges have been allocated in IPv6 for unicast and multicast, along with special addresses for operational support. So this table you have to remember always. You have to keep in mind, especially when you before you go to any exam, especially if for your final, for if let's say you want to make the HCNA exam, also you have to remember all of this, because if you don't remember this, definitely many questions will be lost from you. So normally in the exam, they give you an IP address and they ask you, what is this? Is it reserved for documentation or current global unicast range or whatever? So you have to remember all of these ranges in order to be able to answer. IP addressing for unicast. Okay, for unicast, we have this, am I right? For unicast, we have this. Starts with FE80 for 10 fields of the hosts. Okay, FE80. FE80 is represented like this, if E80, and we can see the other things like this. So this one is directly supposed to be known as a unicast. Okay. So from the first moment, you should be able to answer that this one is a unicast IP address. So global unicast address prefixes are used for public network. So we have global unicast and we have also local unicast. So global unicast is used for public networks. Local unicast is used for local networks. So prefix ranges are reserved for various IP transmission methods. For this here, we have 48 bits, as you can see, 16 bits, and 64 bits. For the global routing prefix, we use the first 48 bits, and the 16 bits will be used for the subnet ID. Then the 64 will be used for the interface ID or the host ID. Okay. So here, this is the representation of this IP address. It can be something like this, and for the unicast, it will be like this. We will have 10 bits for the first field, and here we have the value of 0. Then after that, we will have the interface. So unicast addressing comprises primarily of global unicast and link local unicast address prefixes. However, other forms also exist. All global unicast addresses have a 64-bit interface ID. You see, this is the global unicast. It has 64 bits for the interface ID, with exception to others for which the first 3 bits in the address are zeros. So here we can see 1, 2, 3, 4, 5. We still, okay, I will make it larger here. For here, this one is 64, and this one is the IPv6. How many fields it has? It has 8 fields. So 8 fields means 4 fields for the interface ID, and 4 fields can be used here. 2 fields for the bits for the subnet ID, and what they call it here, the other fields are going to be used for the global routing prefix. So here we have the first, second, third here. Then we have at the middle here, we have 2 fields of zeros. This is how it can be represented. So with exception to addresses for which the first 3 bits in the address are zeros, for such addresses, there is no constraint on the size or structure of the interface ID field. The address format for global unicast addresses comprise of a hierarchy in the form of global routing prefix and a subnet identifier followed by the interface identifier. The global routing prefix is designed to be structured hierarchically by the regional internet registries, RIR, and the Internet Service Provider, ISP, to whom the RIR distribute IP addresses or IP address prefixes. The subnet field is designed to be structured hierarchically by site administrators to provide up to 65 1,535 individual subnets. So to summarize this, they want to say that this regional internet registries, RIR, is responsible to assign or to give IP addresses to the internet service providers. So for every service provider, they can give 65,535 individual subnet masks for every internet service provider. This huge amount of subnets cannot be provided by the IPv4. And in order to do all of this, they have to make it hierarchically. They have to structure the things hierarchically. So they have to use all fields in order to do that. In terms of the link local unicast address, the FE80/10 means that the first 10 bits of the link local address is clearly distinguishable as 1111, 1110, and 10. So if this one is okay, if this one comes to the exam, if they give you this an IP address represented in decimal, then sorry, in binary, then they give you this oh sorry in decimal. This one is no, this one is binary. So if they give you this this value, you have to understand that this one is a unicast. If the IP address started with this value, that means it's a unicast IP address. So the 64-bit interface address range is more than sufficient for the addressing of hosts, and therefore the remaining 54 bits within the link local address are maintained as 0. The example displays the address formats that can be typically associated with each of the common unicast address types. It should be noted also that the third unicast addressing scheme referred to as site local addressing FC00/7. So this one is also what they call it, third unicast addressing scheme. Was originally proposed in RFC 3513. This one is RFC request for comment 3513. This is actually a kind of articles that can be written before the standardization. So they introduced this value to be used for what they call it third unicast addressing scheme. And it may appear in some implementations of IPv6. However, the addressing range has been deprecated as of RFC 4291 and should be avoided as a part of future implementation. Actually, this one was introduced here by this RFC, and then this RFC have deprecated this value, so it shouldn't be used anymore as a unicast format. So from here back to this, as I mentioned, there is one organization called RIR, which is responsible to give IP addresses to the internet service providers. So they fix this, actually, they fix these two parts. The RIR will fix these two parts and will give the 64 bits for the internet service provider to use them freely, Okay, that's all about this. Then here we have the multicast. Multicast actually will be addressed like this. So multicast addresses are distinguished by FF00/8. So FF00 means here this F will be 4 ones, this F will be also 4 ones. So the value will be like this. This one is 8 bits for this value. So this will be fixed. Then after that, we have flags, we have scope, then we have the group ID, which is 112 bits. So address ranges can be like this: FF02 :1. This is for all nodes addresses, link local for all nodes addresses. So this will be sent to all nodes. This one will be sent to all routers. You see here, there's a differentiation. It's not similar to the IPv4. In the IPv4, if we send data to a multicast IP address or broadcast IP address, it will be received by everybody. And also, if we make multicast, so the multicast have to be defined based on the range. So it's not easily defined or distinguished by one value like this. So here, if the end is 1, it will be received by nodes only, and if it ends by 2, it will be received by routers only. So here we can see that the IPv6 is more clear, easy to implement, and also easy to be understood by the network devices. Select multicast address groups are reserved for protocol use. So this one actually is to say that the protocols will decide which one will be used, depends on their needs. So here, a multicast address is an identifier for a set of interfaces, typically belongs to different nodes. A packet sent to a multicast address is delivered to all interfaces identified by that address. So the multicast address range is determined from AF00 :/8 address prefix and is clearly distinguishable from the first 8 bits. So if you find the first 8 bits all ones, that means it's a it's a multicast. So the address architecture for multicast address comprises of flags, scope, and group ID fields. The flags field through 4 bits is currently used to support identification of whether a multicast address is well known as in assigned and recognized by the Global Internet Numbering Authority, or transient, meaning that the multicast address is temporarily assigned. A second bit value is used within the field to determine whether or not the multicast address is based on the network prefix. The remaining higher order 2 bits are reserved and remain set to zeros. So this is the explanations of the flags, the scope, and the group ID. The scope defines a number of potential ranges to which the multicast is applied. Generally, this may refer to a node local scope FF01 or to the link local scope FF02. So here we still have more differentiation here among the multicast IP addresses. So here generally this may refer to a node local scope. So if it starts with FF01, it means this is for the node local scope, and if it's for the link local scope, it would start with FF02, which refers to the listeners within the scope of the link layer, such as an Ethernet segment for which a gateway defines a boundary. Common well-known link local multicast addresses include FF02 :1, which is used to forward to all nodes, and FF02 :2 allows multicast transmission to all router addresses. So here we have to remember this, we have to remember this, also we have to remember this and this. Okay, and in general, any multicast should start with these two. FF, which will give 8 ones at the beginning, at the left side. So if we found 8 ones, that means it's multicast. Then after that, if it's followed by 0, 1, then it means something. If it's followed by 0, 2, it means another thing, and so on. Okay, IPv6 addressing Unicast. As I said, in the IPv4, we have unicast, multicast, and broadcast. But in the IPv6, we have unicast, multicast, and Unicast. Instead of the broadcast, we have something called Unicast. Unicast. So here, Unicast allows multiple instances of a service to be associated with a single address, enabling a variety of service applications. So for the broadcast, if let's say we have broadcast here, from here, it will be sent to everyone. Everyone in the same domain can receive that broadcast. But for the Unicast, we can use the Unicast to allow multiple instances of service to be associated with a single address, enabling a variety of service applications. So as you can see here, this one is one IP address 2001.0DB8, then 84C2. It's the same IP address exactly here. So we can use this IP address for two servers here. It seems that let us read here to understood very well. So Unicast represents an identifier for a set of interfaces. It's an identifier of a set of interfaces. So the set of interfaces can be, one can be installed here and another one can be installed here, and typically belongs to different nodes. This is one node and this is another node. A packet sent to an Unicast address is delivered to one of the interfaces. A packet sent to an Unicast address is delivered to one of the interfaces identified by that address, the nearest one. So here, these two have the same what they call it, the same identifier of the set interfaces. But if let's say this one wants to communicate to the HTTP server, it will directly be routed to the nearest HTTP server here, and this one will be routed to this. Okay, so here the nearest one, according to the routing protocols measure of distance, the Unicast architecture commonly involves an Unicast initiator and one or multiple Unicast responders. I'm sure it's not easy for you to understand, because this one is actually done based on the IB version 6 routing protocols. And in the next class or next topic, we will see the OSPF version 3, which is designed for the IB version 6. So it provides a lot of different things than the IB version 4. The Unicast initiator may commonly be a host that is inquiring to a service, such as in the case of a DNS lookup, or requesting the retrieval of specific data, such as HTTP, web page, and so on. So here they have something called Unicast initiator. The Unicast initiator is have to be introduced in the network of the IB version 6 in order to allow this Unicast to find the nearer server, or to find the nearer destination using the Unicast. So Anycast actually is something similar to the broadcast, but it behaves in different way, depends on the Anycast initiator. And the Anycast initiator actually is not a part of our course, that's why it's not covered here. And also in the HCNA is not covered. We only need to understand how the Anycast looks like and how the IP address, also the structure of the IP address it looks like. Then in this slide, we have something called IPv6 stateless address auto configuration. So hosts are capable of generating IPv6 addresses independently. If you remember, when we have a network of IPv4, then here, if let's say we have a BC here, oh, sorry. If let's say we have a BC here, then this BC is connected to a switch, for example, then this switch is connected to a router, and maybe this one is connected to other BC. So this BC and this BC, let's say BCA and BCB, they cannot communicate unless they have an IB here and IB here. Am I right? In order to get IBs, the IB can be static, can be statically assigned to the machine, which is going to be done manually, or can be dynamic. Dynamic IB. So dynamic IB can be assigned using what they call it, DHCP. DHCP server. So DHCP is a service or a server can be enabled over the router or over the switch or whatever. It depends on, if let's say we have a switch of a layer 3 switch, it can include the DHCP and we can enable it, but this is not the case. Normally the DHCP is enabled over routers, or maybe provided as a DHCP server. DHCP server. So this server can automatically give an IP address to the machines that doesn't have manual or static IP addresses. For the IPv6, if we did not assign IP address to machine A, for example, and if let's say we don't have DHCP here or here, then this machine will generate a random IB. Random IB cannot be used for communication, so it normally starts with 160. If, as I mentioned, if this BC has no BCA, doesn't have a static IP address, and it's set for dynamic, then if let's say the DHCP server is not available in the network, and also the DHCP server service is not enabled on this router, then this machine A is not going to be to get an IP address, a dynamic IP address from any DHCP in the network. That's why it will generate something called a random IP address that will start with 169 point something. But this random IP address is not going to be used for communication. It will not give you any kind of communication through the network. In this case, this BC generates this random IP address which cannot be used for the IPv4 network. In the IPv6 network, they introduce a new solution for this scenario. So if let's say the BC doesn't have a static IP address, and also there is no DHCP service enabled in the network, then the BC can generate something called stateless address auto configuration IP address, which can be used for real communication. So this is one advantage of IP version 6 over the IP version 4. So hosts are capable of generating IP version 6 addresses independently. It doesn't need, it's not necessarily to be statically configured or to be assigned by the HCP server only. It can be independently generated. So every PC can generate its own IP address, which is active, which is able to be communicating through the IP network. So router advertisements deliver network parameter informations. Here. Okay, this is very important info we have to go through. Upon physically establishing with an IP version 6 network, hosts must establish a unique IP version 6 address and associated parameters, such as the prefix of the network. Routers send out router advertisement messages periodically. So all routers will advertise messages periodically, and also in response to router solicitations RS to support router discovery. So used to locate a neighboring router and learn the address prefix and configuration parameters for address auto configuration. So the parameters for the address auto configuration that can be generated by the individual machines actually relies on the advertisement messages of the routers that sent periodically. So the IP version 6 supports stateless address auto configuration, SLAAC. This is the what they call it, the stateless address auto configuration. State, S is coming from state, L is coming from list. This is from address auto configuration that allows hosts to obtain IP version 6 prefixes and automatically generate interface IDs without requiring an external service such as DHCP. Router discovery is the basis for IP version 6 address auto configuration and is implemented through two message formats. So the SLAAC is based on the router discovery, which is explained here. Okay. Router advertisement RA messages allow each router to periodically send multicast RA messages that contain network configuration parameters in order to declare the routers existing to layer 2 hosts and other routers. An RA message is identified by a value of 134 in the type field of the message. Router solicitations RS message are generated after a host is connected to the network. Routers will periodically send out RA messages. However, should a host wish to prompt for an RA message, the host will send an RS message. Routers on the network will generate an RA message to all nodes to notify the host of the default router on the segment and related configuration parameters. The RS message generated by the host can be distinguished by the type field which contained a value of 133. So here we have two things to remember, this value and this value also we have to remember. And also this is the scenario, how it works. So when the PC doesn't have an IP address, how it communicates to the router and how the router is responding back to it. So the first thing here, as you can see, the router solicitation RS will include the ICMP type 133 value. Then the destination will be this one, FF02 double colon 2. This one is for all routers. If you go here back, this one is for all router, multicast for all routers. So the PC here will send a, what they call it, multicast for all routers. So only routers will receive this message. Then the router will reply by the RA that will include the ICMP type 134. Then the source router link local address. Destination is this, because this one is for all nodes. If you go to the previous slide here, it's for all nodes. So the RS is destinating to this, and the RA is destinating to this unicast IP address. And also it will include the data, lifetime, current hop, limit, auto configuration flag, and options like prefix and MTU. So everything will be done automatically without the need of DHCP server or DHCP server steps to be enabled on the network. Then here we have something called EUI64 for IP stateless address auto configuration. This is actually a standard for the stateless address auto configuration. Okay, so a host MAC address is injected with 16-bit FE values, as well as the 7th bit is negated to generate a 64 interface identifier for the IP version 6 address. Okay, let us see here. This one is the MAC address. In order to generate the IP stateless address, this one, in order to generate this, this standard EUI64 says that why we don't use the MAC address of the physical device. So over every network card, we have a MAC address coming from the manufacturer. So if let's say this is the MAC address is 48, am I right? So if this is the MAC address, they said this one, this field, which is 1, 2, 3, 4, 5, 6, 7, number 7, the field number 7 from the MAC address have to be negated. So if it's 0, it have to be replaced by 1. If it's 1, it has to be changed to 0. And also, after this, we separate the MAC address in two parts, 24 bits here and 24 bits here. Then after that, we shift this part to the right and this part to the left, as you can see here. I don't know whether I can draw on the screen or not. Okay, anyway, so this one have to be, this part have to be shifted here, and the other part have to be shifted here. Then at the middle here, at the middle, we have to insert this fields. We have to insert these fields, and the value of this 16 bits have to be equal to FE. So this one is FF and this one is FE. Okay, so we put FF and FE at the middle of the MAC address, and also the bit number 7 have to be changed, has to be negated. So if that field, if that value is 0, we make it 1. If the value is 1, we make it 0. So this is how we can create the the EUI64 interface ID. So here we have how many bits? We have 24 plus 24, it's 48 plus 16, which is 64 interface ID, 64 interface ID. Okay, This is how it works. In order to facilitate communications over an IPv6 network, each interface must be assigned a valid IPv6 address. The interface ID of the IPv6 address can be defined either through manual configuration by a network administrator, generated through the system software, or generated using the IEEE 64 bits extended unique identifier, EUI64 format. Due to practicality, the most common means for IPv6 addressing is to generate the interface ID using the EUI64 format. This standard uses the interface MAC address to generate the IPv6 interface ID. The MAC address, however, represents 48 bits address, whilst the requested interface ID must be composed of 64 bits values. The first 24 bits expressed by C, this one, of the MAC address represent the vendor company ID, while the remaining 24 bits expressed by E, this one, represents the unique extension identifier assigned by the manufacturer. The higher 7th bit in the address represents a universal local bit to enable interface identifiers with universal scope. So where this value is 0, the MAC address is unique globally. During conversion, this standard process inserts 2 octet, this one, 0xFF and 0xFE at the middle, values totaling 16 bits between the vendor identifier, which is the first 24, and the extension identifier, which is the other 24 for MAC address, and the universal local bit 0 is changed to 1 to indicate that the interface ID now represents a globally unique address value. A 64-bit interface ID is created and associated with the interface prefix to generate the IPv6 interface address. So that's all about the stateless address auto configuration. So here we understood how it can be generated, then how it can be how it can use the EUI64 standard to generate the interface ID from the physical MAC address. So here is the way of the IPv6 stateless address auto configuration. We have something called DAD. DAD actually is the duplicate address detection. Duplicate address detection. It's used in IPv6 to verify that an address is unique before it's applied to the host interface. So after we generate the stateless IP here, we have to check whether it's unique or not. If it's a unique IP address, then we can use it. Otherwise, we have to change it. Okay, so how we can check the uniqueness of the IP address is using this feature, DAD, which is the duplicate address detection. So here we can see that this BC tentative sends an ICMP type 135. Don't confuse yourself. Here they use 133 and 134. For the DAD, they use 135 and the reply will be 136. So here the source is unknown. Destination is FF02, which is for all routers. Is it for all routers? This one, FF02 ends by 1. This one is for all nodes. So every node will receive this, then should reply. So data is this, and the query is this address is in use. Is this address in use? Then if this guy have the same IP address will send a message with the 136, will say that, yes, I'm using this address. So you cannot use here. This PC cannot use this address. But if let's say this IP address is unique, then every node connected to the network will reply, yes, this IP address is not in use. So you can use it. This is how it works. It's very simple, actually, very simple idea. Let us go through this. Before an IP address, IPv6 unicast address is assigned to an interface. Duplicate address detection is performed to check whether the address is used by another node. DAD is required if IP addresses are configured automatically. So this DAD have to be used whenever we use the stateless IP addresses. An IPv6 unicast address that is assigned to an interface but has not been verified by that is called a tentative address. So before we do verification for the IP address, it's still a tentative address. An interface cannot use the tentative address for unicast communication, but will join two multicast groups, all nodes multicast groups, and solicited node multicast group. A solicited node multicast address is generated by taking the last 24 bits of a unicast or anycast address and appending the address to the FF02. You can see here, this one, prefix in the case where the address is 2000:1 is used, the address solicited node multicast address FF02:1 FF001 would be generated. So this is how the DAD works, and how the tentative IP address is going to be used for multicast or unicast automatically, even if the IP address is not a unique IP address. IPv6 that is similar to the gratuitous ARB, gratuitous ARB protocol used in IPv6 version 4 to detect the duplicated IP version 4 host addresses upon address assignment or connection of the host to the network. A node sends neighbor solicitation in its message that requests the tentative address be used as the destination address to the solicited node multicast group. If the node receives a neighbor advertisement in a reply message, the tentative address is confirmed as being used by another node, and the node will not use this tentative address for communication, following which manual assignment of an address by an administrator would be necessary. So to summarize all of this, in the IP version 4, we have something called gratuitous ARB protocol that's used to detect the duplicated IP addresses. If in case we assign a static IP address manually, then somebody else is using the same IP address. So the gratuitous ARB protocol can detect the duplication of that IP address. But in IP version 6, they use something called DAD. That's all about it. And here is the summary. So in the summary, we have two questions here. What is the smallest condensed IP version 6 value possible for this address? So here, let us take this example and make it condensed. So this is the IP. As I mentioned, the IP, it will be like this. Then we have to remove this leading 0. We have to keep this. And here we put 0, 0, 0, 0. So this 0 is for this 0 is for this 0 for this field, this 0 for this field. Then after that we have to take this and we have to remove this leading 0, and after this we take that like this, and should we remove this 0? Definitely no, because zeros at the right side we cannot remove. We can remove only zeros at the left side. So this is the first stage. Then after that we can take this, we still can condense this to be like this. So this is the shortest IP address we can have for this example. So how is it possible for an end station to independently generate an IP address? Definitely using by using what they call it EUI 6064 stateless auto configuration auto. Okay, this is the answer for the second question, and that's all for today. Okay, guys, and see you inshallah next week. Assalamu alaikum and have a good day, inshallah.